What specific problem does your proposed method address in the context of novel view synthesis, and how does it improve upon existing methods, particularly in terms of extrapolation capabilities?
Our proposed method addresses the challenge of synthesizing novel views from unposed reference images, particularly focusing on the limitations of existing methods in extrapolation capabilities. While previous feed-forward and generative approaches excel in interpolative settings, they struggle with synthesizing occluded or unseen regions, especially when the target viewpoint lies outside the convex hull of reference camera positions. By leveraging warping and inpainting techniques and introducing cross-modal attention installation, our method effectively combines geometric conditioning from multiple reference views to guide the generative process, enabling robust synthesis at arbitrary viewpoints. Additionally, our proximity-based mesh conditioning enhances the quality of generated images and geometries by filtering out erroneous projections and incorporating depth and normal information, which significantly improves performance in extrapolative scenarios. This results in aligned colored point clouds and state-of-the-art performance in extrapolative camera settings, demonstrating our method's superior generalization capabilities compared to existing approaches.
Can you explain how your proposed method works step by step, including the role of the image reference network, image denoising network, geometry prediction model, and the process of cross-modal attention distillation?
Our proposed method operates in a multi-step process to achieve novel view synthesis and geometry prediction from unposed reference images. First, the image reference network extracts semantic features from the input reference images, which are essential for understanding the scene structure. Next, the geometry prediction model utilizes these reference images to generate corresponding camera poses and point maps, which represent 3D point coordinates for each pixel. The projected point map is then used as a sparse geometric correspondence condition for the image denoising network, which synthesizes the novel view image by leveraging both the target and reference correspondence conditions. To enhance the alignment between the generated image and its geometry, we implement cross-modal attention distillation, where the spatial attention maps from the image denoising network are integrated into the geometry denoising network, allowing it to benefit from the rich semantic features of the image domain while maintaining deterministic geometry completion. This synergistic approach ensures that the generated images and geometries are consistent and accurate, even in extrapolative scenarios.
Please provide a detailed example to illustrate how your algorithm performs novel view synthesis from multiple unposed reference images. Walk through the main steps with this example, describing each component's contribution to the final output.
To illustrate how our algorithm performs novel view synthesis from multiple unposed reference images, consider a scenario where we have 3 unposed reference images of a scene. The process begins with the extraction of semantic features from these reference images using the image reference network, which captures essential information about the scene's structure and appearance. Next, we employ an off-the-shelf geometry prediction model to obtain corresponding camera poses and point maps for each reference image, merging these into a single point cloud. The key step involves projecting this point cloud onto the target viewpoint, creating a projected point map that serves as a sparse geometric correspondence condition for the image denoising network. This network then utilizes both the projected point map and the reference point maps to generate a novel view image through aggregated attention, allowing it to establish spatial correspondences across all reference images while ensuring consistency in the generated output. Additionally, we enhance the process with proximity-based mesh conditioning, which refines the projected point map by filtering out noise and erroneous projections, ultimately leading to a high-fidelity novel view synthesis that aligns well with the generated geometry.
What are the key advantages of your approach compared to traditional methods for novel view synthesis, particularly in terms of performance on extrapolative tasks and zero-shot generalization?
Our approach offers significant advantages over traditional methods for novel view synthesis, particularly in extrapolative tasks and zero-shot generalization. Firstly, by leveraging warping and inpainting methods and cross-modal attention installation, we enable synthesis at arbitrary viewpoints from unposed reference images, overcoming the limitations of traditional methods that struggle with occluded or unseen regions. Secondly, our method achieves geometric alignment with reference geometry, effectively addressing scale shift discrepancies that often hinder depth prediction in conventional approaches. Additionally, the incorporation of proximity-based mesh conditioning enhances the robustness of our generated outputs by filtering out erroneous projections, which is crucial for maintaining accuracy in extrapolative settings. Finally, our results demonstrate state-of-the-art performance in extrapolative camera settings while maintaining competitive reconstruction performance, showcasing our model's ability to generalize effectively to unseen data without requiring extensive retraining.
Describe the validation process you used to test your method's effectiveness. What datasets were utilized, and what metrics did you employ? How do these metrics demonstrate the success of your method?
To validate the effectiveness of our method, we conducted quantitative ablation studies using the real estate 10K dataset, specifically under extrapolative settings. We assessed the contributions of various components of our approach, such as geometric conditioning and proximity-based mesh conditioning, by comparing performance metrics across different configurations. The metrics employed included image quality and geometric accuracy, which were evaluated through progressive performance improvements observed in the results. These metrics demonstrate the success of our method by showing that the introduction of additional conditioning techniques, like cross-modal attention distillation, leads to enhanced synthesis quality and alignment between generated images and geometries. Furthermore, our model's ability to generalize to varying numbers of input viewpoints further underscores its robustness and effectiveness in novel view synthesis.
What limitations or potential challenges does your method face, particularly in handling large occluded regions or noisy projections, and how do you plan to address these in future work?
Our method faces significant challenges when synthesizing large occluded regions, as the image inpainting network struggles to generate plausible content in areas with no reference projections. This limitation arises from the inherent ambiguity in extrapolative scenarios, where the image generation pipeline encounters difficulties due to partial observations. Additionally, the proximity-based mesh conditioning addresses issues related to noisy projections from sparse point clouds, which can lead to misalignment in the generation process. To mitigate these challenges, we propose to enhance the conditioning process by incorporating depth and normal maps from the mesh representation, allowing the network to prioritize reliable correspondences and filter out noise. Future work will focus on improving the robustness of the image inpainting network in extrapolative settings and further refining the mesh conditioning to better handle erroneous projections.